find it here. Okay, so 3 puzzles. Objects with different masses fall with the same acceleration. Acceleration feels like gravity. And there's 2 different types of mass, gravitational mass and inertial mass. They're always the same. So let's talk about the first 2 are really strongly related to one another. So the idea is that if we want to talk about the inertial mass, then we're talking about Newton's famous formula, which says acceleration equals force divided by mass. Often that's written F equals ma, but I like to write it as A equals F over m to emphasize the cause and effect relationship. In other words, acceleration is caused by force, and by an object of mass m, inertial mass m really, because of the fact that they're always the same, we usually just say the mass. If I have an object of mass m, then the acceleration is, I'll put like an m sub I there to mean inertial mass here, is the force divided by the inertial mass. That's what we mean by the inertial mass. It's the property of an object that gives it inertia, that gives it resistance to acceleration. Whereas gravitational mass describes how gravity acts on an object. That's what its gravitational mass represents. So gravitational mass is what shows up in Newton's law of gravity, where if I've got 2 masses, and I'll call this one big M and this one little m, and I'll put little g's on them to say we're talking about gravitational mass here, then the gravitational force on either one has magnitude capital G, that universal constant of nature, the gravitational constant, times the product of the masses divided by r is the distance between them, divided by r squared. So the remarkable fact, although we will explain it, is that an object's inertial mass and its gravitational mass are always the same. And where this shows up very directly is if we have an object in the vicinity of the surface of the planet, let's say Earth, then for Earth here, if I let m sub O plus there be Earth's mass, that's a common symbol for the Earth, is O plus like that, and r here, r sub O plus r sub Earth is the radius of the Earth, and I have something of mass m near the surface, then the gravitational force on it will be g times the mass of the Earth times the mass of the little object. I'm not going to bother with the gravitational subscript right now, divided by the radius of the Earth squared. And that quantity right there, if you evaluate it for Earth, is what we call little g, which is 9.8 meters per second squared, the acceleration due to gravity at Earth's surface. And so we can say that the gravitational force on an object is mg, its mass times the acceleration due to gravity at Earth's surface. If we were on Mars, we would plug in the quantities for Mars and get a different acceleration due to gravity at surface. It's only about 40% as large as ours, which is why astronauts on Mars would weigh less than they do on Earth. That's why astronauts on the moon weigh less than they do on Earth, because the moon's acceleration due to gravity, g times the moon's mass divided by the moon's radius squared, is only 1/6 as big as that same quantity for Earth. And so if I want to figure out what is the acceleration of some object near Earth's surface, then there it is, mass m force on it will be mg, but that will also be its mass times the acceleration. And this first piece there, we're using its gravitational mass. How does it couple to gravity? The thing that you multiply the acceleration due to gravity by in order to figure out what the force on it will be. But on the second side over here, we're using the inertial mass, the property of it that describes how much it resists acceleration. But m is on both sides here, and so you can cancel it out. And if the gravitational mass and the inertial mass are equal to one another, we get that the acceleration of any body, no matter what its mass is g in the vicinity of Earth's surface. It doesn't matter what the mass is, because if I had an object with twice the mass, what happens to its gravitational force on it? First of all, what do we call the gravitational force on something? What's the W word that we use to mean the gravitational force on it? It's weight. Its weight is the gravitational force on it. So if something has twice as much mass, what happens to its weight? It's how many times bigger? Twice as big. It's always twice as big. If I have twice as much mass, it's always twice as big. Now, normally you don't even think about this. We just say the mass, but what I'm trying to point out here is that we're really talking about what could be two different things. Here I could put in subscript again. I probably should have just been more consistent, but the gravitational mass is what tells you what the gravitational force on it. The inertial mass is what tells you how it responds in terms of acceleration to that force. And we're assuming we can cancel these quantities out. We're assuming that the gravitational mass and the inertial mass are always the same. What questions do you have, including, I don't know what to ask, that could happen here. That can always happen. Yes?
So we know that the masses would be the same because of multiple experiments, I guess, finding the constant acceleration.
Yeah, anytime we do an experiment, essentially, you know, you could if I drop a hammer and a feather, okay, the hammer is going to get to the ground faster, but that's just because the feather feels air resistance. There's a famous experiment done on the moon where an astronaut on Apollo 15 dropped a hammer and a feather, and whoop, it went down to the surface in tandem. You can do that on Earth by evacuating a chamber. You can take the air out of a chamber, and you could drop lots and lots of things and always find that they had exactly the same acceleration. If you do the experiment, we never find an exception to where everything has the same acceleration due to gravity. As long as, now, you know, you couldn't drop Jupiter onto Earth. That doesn't make any sense. But in other words, as long as you're dealing with something which is way less massive than Earth, then they'll always have the same acceleration due to gravity, and that relies on this cancellation right here, that the mass that you use to figure out how it responds to, how the acceleration responds to forces, and the mass that you use to determine the gravitational force on it always is the same. You can always cancel them out. So could you conceive of a situation where they could be different? Like, how would we be able to tell that they were different? What could you do there? Could I have two objects that had, say, the same gravitational mass but different inertial masses? Never happens, but I'll tell you an experiment where you could, in principle, see a difference. And like I said last time, when I first encountered this idea, I was puzzled as to what the big deal was, because I just thought, well, there's just the mass. And so, since there's this thing called mass, and it both tells how much weight's going to have, something's going to have, and tells how it's going to respond to forces, well, then they're just equal. But what I want to try to impress upon you is that in principle, they could be different. So, suppose that I had two weights, okay? And one of them was painted, let's say, red, and the other one was painted blue. And I put them both on a scale, and I discover that they weigh exactly the same thing. The scale gives me exactly the same reading for both of them, okay? So what have I determined by doing that? Have I measured their inertial masses, or have I measured their gravitational masses by putting them on the scale? Which one is that? So I put them on the scale to see what they weigh. The weight is the gravitational force, so that would be determining the, what kind of mass? Inertial or gravitational? Gravitational, because it's telling us how it couples to gravity, how it feels the effects of gravity. So I've got a red block, let's say, and a blue block. Put them both on a scale, they weigh exactly the same thing, all right? Now, suppose I did something different. So I kind of want to write it out. Take a red block, a blue block, put them on a scale. And find that they weigh the same. Conclusion, their gravitational masses are equal. Because that's what weight is measuring. Okay, now here's how you can do something that depends on the inertial mass. Attach the block to a spring. Attach it to a spring. And pull on the block so that you stretch the spring beyond what its equilibrium length would be, the length the spring has if it's just sitting there. So if I do that, if I pull that, then if I let go, the spring is exerting a force on it. So if I let go, what's the block going to start doing? It will in fact oscillate. So physics people don't answer these questions right now. I mean, I appreciate it, but I'm trying to, I'm targeting more the folks who are not physics majors so that they, I want to see if they're, kind of following along. If I were to stretch the spring, if you stretch it, pulls back on you, right? You can feel it pulling back on you. So if you let go, the spring will be pulling on the block, and so the block will start moving as a result of that. Does that make sense? Okay. Now, in fact, you might have experience with springs where what will happen is it'll start moving, and then it'll start to compress the spring, and the spring starts pushing forwards on it instead of backwards. And so it will slow down, turn around, start coming the other direction. It'll stretch the spring, which will make the spring pull it back. It'll compress the spring, which will make the spring push it forward. And so what happens is that the block starts to oscillate back and forth. It'll jiggle, basically, back and forth. Okay? If we pull on the block and let go, the spring will cause the block to oscillate. To jiggle back and forth. So what does your intuition tell you? Which would jiggle faster? a low mass block or a high mass block, which one would jiggle faster? If I put a lower mass block there versus a higher mass block, which one will jiggle back and forth faster? Again, not physics, not astrophysics. Which one would wiggle faster? Let me put it this way. If this is a 1 kilogram block, I let it jiggle. Then I put a pickup truck there. Pull back on the pickup truck, assuming I can overcome friction and so forth. Let it jiggle. Is it going to be the pickup truck is going, and the 1 kilogram block is going, or is it going to be that it's the pickup truck that's going, and the 1 kilogram block is going, which one would it be?
The second one.
The second one, yeah, absolutely.
And that's because of their inertial mass, I'm assuming?
Because of the different inertial masses. It's harder to accelerate that massive pickup truck than it is the 1 kilogram block. And so the oscillations will take place at a higher frequency for a smaller mass and vice versa because of the different inertial masses. So the greater the inertial mass of the block, the harder it is for the spring to accelerate it. So the oscillation frequency will be smaller in other words, fewer oscillations per unit time for the more massive block, for a more massive block. And notice this has nothing to do with gravity. We could do this in outer space. You could attach a block to a spring in outer space, stretch it, and the thing would jiggle back and forth. You don't have to be on the surface of the earth. This is strictly horizontal motion, so the weight of the block is balanced by an upward force from the floor. And in the horizontal direction, gravity is not involved. All that's involved is the force that the spring is exerting on our block. So we took our blue block and we took our red block, and they weighed exactly the same. So what will we find in the real world if we attach them to the spring? If they weigh exactly the same thing, and we attach them to the spring, compare their oscillation frequencies, compare how fast they'll vibrate. If the two blocks weigh the same thing, will they vibrate at the same frequency or a different frequency? The same, yeah, the same. Because we always find in the real world that if you measure a block's inertial mass and you measure its gravitational mass, they always come out the same. But imagine that they didn't. Imagine that you had a red block and a blue block and they weighed the same, and then you attached them to identical springs and stretched them, and they jiggled at different frequencies. That would have allowed you to determine that you had two objects whose gravitational masses were equal, but whose inertial masses were not equal to one another. So what I want to convince you is that you could, at least in principle, do an experiment that would show you that two things that had the same gravitational mass responded differently to other forces, responded differently to the spring, exerting the same amount of force on each of them for a given stretch of the spring. So Einstein was puzzled by this. Einstein was puzzled by the fact that we always find that the gravitational mass and the inertial mass are always the same, because really we're determining them via two fundamentally different things. So, I hesitate to ask, but does that make sense? Do you see what I'm getting at? That there are two different types of mass, essentially, that we can imagine measuring, and that they always turn out to be the same, so that we can say, okay, well, there's just mass, but somehow inertial mass is also what determines how strongly something responds to gravity. This very different property called inertial mass somehow is also the same thing that allows things to respond to gravity. What questions do you have, including what? I'm trying to see if you see the point, and everybody's just staring at me. So I'm trying to find out if you see the point or not. I feel like I'm pulling teeth right now. Do you see the point? You think so? Do you see the point?
What point should I be seeing?
Okay, good, thank you. The point that you should be seeing is that in principle, at least, you can imagine a world where gravitational mass and inertial mass were not equal. You can imagine a world where I could weigh two things, find out they weigh the same, so they have the same gravitational mass, that whatever quantity it is that makes them respond to gravity is the same for both of them. And then I could attach them to identical springs and find out that they don't oscillate at the same frequency, which would tell us their inertial mass, their property that determines how hard it is to accelerate them, were different from one another. In principle, I could imagine a world where that would happen. That's the point I want you to see. That I can do an experiment that would show that it was different. And yet, in the world we live in, that would never happen. If I weighed two blocks and they weighed the same thing, they'll always jiggle on identical springs at the same frequency. They'll always respond to inertia in the same way. If they have the same weights, if I apply a given force to both of them, they'll accelerate it exactly the same way, even if it's not a gravitational force that I'm applying to them. Yes?
So is that not because they're the same shape and the same material?
No, no. Let's say that one of them is made of iron and the other one is made of styrofoam. I could do that too. I mean, the styrofoam block's gonna be much bigger. But in other words, or you could have just two human beings that weigh the same on the scale, also have the same inertial mass. If you put a rope on them and pulled them, they would be equally hard to pull, both of them. If they weigh the same, they're both equally hard to pull. Two things that have equal, if I have two objects and one weighs more, I will always find it's harder for me to shove it, harder for me to move it. If I took it into outer space, the one that weighed more on Earth would be the one that was harder to shake around and shove in outer space. But you could imagine that the one that weighed more on Earth, you get into outer space, and that's the one that's easier to shake around. It would never happen, but at least you can imagine that happening, is what I'm getting at. Are you buying what I'm selling?
I'm buying it.
You're buying it, okay. Did you have a question, Chase?
Oh,
Or you just
no.
kind of stretching, okay. All right. So, what is going on here? Well, Einstein said that the happiest thought in his life was that if you were in an elevator that was simply freely falling, like the cable snapped or whatever, then you would not feel your weight. And this, he said, led him ultimately to general relativity. So we're going to give two ways to state the principle of equivalence, the equivalence principle here, and use it to figure out why, according to Einstein and general relativity, it's natural that gravitational mass and inertial mass are always the same. And ultimately what we will decide is it's because gravity isn't actually a force. The quote-unquote force of gravity is not actually a force. It's a consequence of observing an object in what we call a non-inertial frame of reference. So, two ways to state the equivalence principle of equivalence. One, in a volume of space is small enough that the gravitational field can be assumed constant within it, the downward pull of gravity can be duplicated by an upward acceleration of the observer. In other words, no experiment would allow an observer in a closed compartment such as the one shown in the preceding figure. It's actually a coming figure. The one shown in a figure that's going to be on another slide to know which of the two situations he was actually in. So let me skip forward and show the situation here. So we've got a person sitting on the surface of the earth reading a book in a room with a lamp, and then imagine that space aliens have actually kidnapped that person and put him inside of a closed compartment so he can't see what's outside. That's just so that he can't just say, oh, I'm in outer space by looking outside. It's not particularly important that he not be able to see outside, other than he would know that he'd been kidnapped by space aliens if he could see outside. You put him in that compartment, and instead of being on the surface of the planet, what's actually happening is it's accelerating upwards, if you will. There's no up or down in space, but we'll say up is the ceiling, down is the floor of the room, so it's accelerating upwards at 9.8 meters per second squared, which happens to be what the acceleration due to gravity is at Earth's surface. The assertion here is that the guy in the room would have no way of telling which situation he was actually in. Now, if you were in a rocket, you'd feel the rockets firing. Rockets aren't perfectly smooth, but if you had this super nice ion engine or something like that, where you just couldn't feel any shaking or anything like that, you would not be able to tell which of those two situations was in. If your compartment was in outer space, accelerating from floor to ceiling at 9.8 meters per second squared, or if you were on the surface of the Earth. So, in formal terms, it's that top one there. A volume of space small enough that we can assume the gravitational field is constant within it, such as this room, right? So the ceiling is a little bit further from the center of the Earth than the floor is, but not a lot compared to the Earth's radius. So it's awfully close to being true that the force of gravity, as the quote-unquote force of gravity on something at the top of the room, is very nearly the same as it is on something at the bottom of the room. So we can assume that the gravitational field inside of our room is essentially perfectly uniform. What we're saying here is that if some space aliens had drugged us all, and then we woke up in this room, we could be in outer space accelerating upwards at 9.8 meters per second squared, and nothing we could do, no experiment we could perform in this room would tell us that we weren't actually on the surface of the Earth. That's one version of the principle of equivalence, and I'll say some more about that as we go along. The other version is the effects of gravity are eliminated in a freely falling frame of reference as long as the volume of space considered is small enough that the gravitational field can be assumed to be uniform inside it. In other words, no experiment would allow an observer in a closed compartment to tell whether she was far away from any stars and planets where there's essentially no gravity, or she were falling freely in a uniform gravitational field. So let's talk about the first of those in some more detail. So, let's see. If I take something that I don't care about, okay, this eraser. I'm not worried about dropping this eraser. All right? So, if I let go of this eraser, what is it going to do? It's going to accelerate towards the ground. What is its acceleration? 9.8 meters per second. Every second it's going 9.8 meters per second faster than it was 1 second before. I let go of it, it falls to the ground. Okay. How does Newton explain the fact that it falls to the ground? According to Newton, why does that fall to the ground? Physics people can answer now. I'm looking at that restriction. It falls to the ground because there's a what on it? A force of gravity. So Newton would say, well, there's a force of gravity on it, and so therefore it accelerates in response to the force of gravity. Now, I step on a scale. Step on a scale, and that compresses actually often. It compresses a spring inside the scale, and how much it compresses that spring tells me how much gravitational force is exerted on me, such that the weight, what am I trying to say? The weight is telling me how much gravitational force there is on me, right? So I step on a scale, and I'm pushing down on the scale, and it has to push up just as hard on me, and so when there's an equilibrium there, it tells me what my weight is. So it's measuring the gravitational force on me. All right, now, first imagine that we go into outer space, and the compartment is not accelerating, it's just drifting through space. Engines off, just drifting through space. If we're just freely floating through space, and I let go of this eraser, what will it do?
Sit there.
It'll just sit there, right? It'll just hover there, because if we're just freely floating through space, is there any force on it? No. And so therefore, it'll happily obey Newton's first law, which says it'll move in a straight line at constant speed, and if it's not moving at all, then straight line at constant speed means just sitting there. The straight line part goes away because it's just sitting there. So it would just float there, okay? If I were to throw the eraser, how would it move after I let go of it? If I'm drifting in space, how would the eraser move? It would fly away in a
Straight line as it should go.
straight line at constant speed because there's no force on it, and so there would be no acceleration. It would just fly away from me in a straight line at constant speed. If I'm floating in outer space and I step on a scale, do I weigh anything? No, I don't, because if I'm just floating in space, I could just hover right above the scale and gently put my feet on it. I don't push down on it in any way, so the scale doesn't read anything. So I don't weigh anything on the scale if I'm just floating through space. Did you have a question, Chase?
No, I
You're right, huh? Okay, right, okay. Now, turn on the rockets so that the compartment is accelerating upwards at 9.8 meters per second squared. So, if somebody was outside, okay, so let's let people be able to see inside. Somebody was outside watching me in that now compartment accelerating upwards at 9.8 meters per second squared, and I let go of the eraser, then they will see that the eraser has no force on it after I let go of it, right? So how will it move as a result of that?
the same speed as it should go.
It will keep going the same speed it did as it was right before I let go of it. That's absolutely right. It'll just keep moving at the same speed that it was going right before I let go of it. To make things a little simpler to visualize, let's say that you turn on the rockets, and so it starts to accelerate. And right at that moment that the rockets are turned on, I let go of it. And there's a person floating outside, initially at rest with respect to the compartment. So in that situation, they'll see that the eraser doesn't move at all after I let go of it, because there's no force on it, and it wasn't moving at the instant I let go of it, and so it's just sitting there. But the floor is accelerating upwards at 9.8 meters per second squared, right? The floor is accelerating upwards. So as seen by the person outside, I let go of this, and it continues to just hover there, but what's the floor doing?
Moving up.
So the floor is going to come up and crash into the eraser. The floor is going to accelerate up and hit the eraser as seen by somebody outside the compartment. But what do I see inside the compartment when I let go of it?
falling.
I see it falling, because if the person outside sees the floor come up and smack the eraser, what it has to look like to me is the eraser accelerates down towards the floor at 9.8 meters per second squared. So I'm gonna say, that's just what would happen on the surface of the Earth. It behaves exactly the same way in the accelerating compartment that it would on the surface of the Earth. Suppose that I step on a scale in the accelerating compartment. So I step on that scale. Am I accelerating?